briefly, I'm going to say this part of this work is have a couple works in collaboration with Luce Teresa, Lucero, and also with Rodrigo Lecaro from Universidad Federico Santa Maria and Ariel Perez, who is an PhD student. He will present their PhD thesis in the next month, I hope. Okay. Their results are part of this conference. Okay. Well, I'm going to try to talk not too technically because the results are very technical, but I'm going to try to explain which are the main ideas behind this kind of problem. The first, why are interesting to talk about the discrete problems, about how we can talk about a few about the well-known Calderon problem and also an application for a BBM equation. Okay. Finally, why we are interested into study this problem because it's clear that there are a lot of people which take a PDE and put inside the computer and want to have some numerical result. This is classical, and it's quite natural to put some question when you have a discrete problem. The main thing is when the size of the mesh go to zero, the question is the discrete problem converts to the continuous one. It's very natural question. We don't have all time an easy answer. This is the main problem. Okay. For instance, in the continuous case, for the Laplacian, for instance, which is the most friendly operator, we have a lot of properties. Unique continuation property. There are a lot of people who will talk about controllability in PDE. Inverse problems is a very important area of research in the last years, and for that reason, we want to obtain some results of identifiability, stability, numerical reconstruction, and so on. Or when we are thinking in a control problem, we want to looking for the minimum of the functional, and the question is what happens when we go to the discrete one, and so on. There are a lot of problems. For that reason, the main question all time is: I have a discrete problem, I have a continuous one, and the question when the h goes to zero, what happens? Okay, and this is a few the idea of this question. This question is not new. This is a very old question, but there are a lot of open problems now. Okay. I'm going to start with the classical Calderon problem. Okay, I don't know if everybody is familiar with the inverse problem, but here's a picture of Professor Alberto Calderon and Professor Calderon in the 80s in a congress in Brazil, in Botafogo, in LNCC, put a very simple question. The question is, I have an equation, the divergence of gamma gradient u equals 0 in omega. Omega is an open set, and u is equal f in the boundary. And the question, in this case, gamma represents the potential function, but excuse me, u represents the potential function, and gamma is the electrical conductivity of a wire. And the main question is, it is possible to reconstruct the conductivity measuring only on the boundary? That's the mathematical question can be put in the following way. We can define the so-called Steglov-Poincare operator. That means if I put F, I can compute U, and then since I have U, I can compute the Neumann condition. Okay, and the question is, in this sense, we can define this operator, but the question is at the inverse. The inverse means if I know all the measurements, is it possible to recover the conductivity? This is the question. Okay, and in inverse problem, the people put several different questions. The first one is the injectivity. That means if all the measurements in the boundary are equal, that implies that the conductivity is equal. That means if I have two different material, if it's possible to obtain the same measurement for two different material. This is the first question. The second one is if the measurements of the boundary are similar, what we can say about the conductivity. The conductivities are similar. This is so-called the stability. Of course, the people want to recover gamma from the measurement. These are the typical four questions in inverse problem. Okay, The questions are quite simple. The answer is very hard. This is the principal thing here. Okay, and there is a long history of this work. There are a lot of journal called inverse problems. For that reason, it's a very productivity area of research. But the first work is from Calderon in 80s, and appear several ones of Convocelius, Sylvester Ullman, Alessandrini, where the people begin to give some answers about the uniqueness, that means that means the stability, the identifiability results, but in all cases appear some consideration. For example, the identifiability is true, but not for all measures, not for all conductivities. The conductivity needs to be enough regular. In this case, is C2, and not for any dimension. Dimensions need to n bigger than 3. Later, Alessandrini presented a very important result about the stability. The stability is good, but it's logarithmic. That means if the inequality have the logarithm. The logarithm is very bad for numerical. It's very poor. Okay, and of course there is a very important work of Sala and Paivarinta in 2006, where they say the stability is true for gamma only in L infinity, but this is only for dimension 2. For dimension 1, the result is false. Okay, in this case, if the dimension is bigger, the results are better. Okay, and they present Asala, Mueller, Pavarinta, and Seltanen present some method for numerical reconstruction called complex geometric optics. Okay. These are some of the problem, some of the results, but there is a very big history for this kind of problem, for different models, for elasticity, for fluids, and so on. But when we want to recover this, we want to say, well, is this true for when we pass to discrete equation? What means discrete equation? The question is, I'm going to write the PDE, but in terms of the finite difference, for instance. I'm going to write the Laplacian, but the Laplacian in finite difference. Okay. Well, why we are interested in unique continuation properties? Because the unique continuation properties are very well related with controllability and with the inverse problem. For that reason, a lot of people who were in control now work in inverse problems. The community is almost the same. A lot of friends are appear in these things. Okay? Well, which is a unique continuation property? This is the first thing. Well, we can consider P is a differential operator. You can think it's a Laplacian. And you have then an equation PDU equals 0. That means Laplacian of U equals 0. And you say, well, what happens is U is equal 0 in some part of the domain. Then you can say, the unique solution of the Laplacian with vanish in an open region is U equals 0. This is the classical unique continuation property. Okay, that means I have an equation. I put some condition on the function, on the solution of the problem, and the question is this condition is enough to obtain only that the unique solution of the problem is 0. That happens with the Laplacian. Okay, but what happens when you go to the Laplacian in finite difference? Okay, you can think the classical contraction of the finite difference. Okay, the progressive finite difference, or as you want. Well, the first thing is the result is false. You can have a solution. You can write the equation of the Laplacian, the scale Laplacian U equals 0 in a square. You can put U is equal 0 in one part of the boundary, but you don't have the same result of the continuous one. Why? Well, the problem is when you go to you study what happened with the spectrum of the operators, the discrete operator and the continuous operator that don't have the same eigenvalues. Okay, and appear some eigenvalues that do not converge to the continuous one, and this is the main problem. Okay, in particular, there is an example in the works of Suasua or Tarek or another, that they can find some Laplacians, some eigenvalues of the discrete one in this way does not converge to the eigenvalues of the continuous one. Okay, this produced a lot of problems, and this made that the unique continuation property does not do not hold in the case of the discrete one. Okay, for that reason, the answer is not too completely simple. Okay. Well, what happened with the continuous one is, well, there are a lot of people who take attention in this kind of problems and begin to study what happened with the inverse problem. Okay, for instance, there are some works of Sylvain Herbedosa, Lucie Boudouin, Frank Boyer, Jérôme Larousset, and people related with these teams. Okay, where they begin to study inverse problems in 1D and discrete Kahneman estimates. Okay, well, what is Kahneman estimate? I forgot to say that. Kahneman estimate is a quantitative estimate to prove and this kind of estimate give you as a consequence a unique continuation property. And the Kahneman estimates are very well used in inverse problems, and all the community of controllability know very well this Kahneman estimate. Okay, and they begin to study several words of this one. Okay, and there are some cases on 1D and for controls where the people say, yes, the unique continuation property does not hold in the same sense of continuous because there is some restriction related with the size of the mesh. Okay, that's the main problem here. Okay, well, uh, I'm going to try to pass not to. I'm going to pass a few fast because I'm going to tell you a few more, which is the idea of the result. The proofs are very hard to explain in a in a short lecture, and for that reason, I'm going to try to give you the main ideas. If somebody is interested, please feel free to ask, and you can share the works. Okay, but we can think we will have a very simple case. This we're going to take a square, for instance, a square is 0, 1, 0, 1. Okay, I'm going to see finite difference and a complete regular mesh. This the mesh, each piece of the mesh is a square. Okay, this is and all is the same size. The size of every step is h, where h is 1 over n plus 1. Okay, I'm going to make a small grid. Well, but here begins to appear the problem because when you make the computations, you don't need only work in this mesh, but you need to define another kind of mesh called a mesh. That means a mesh will consider the middle points of the mesh. Okay, and this dual mesh is going to call a W star. Okay, and we need to define these points. In this sense, we have something like this. This is our mesh in square, but we need to consider the middle points in all mesh. Okay. Well, what is the idea? The idea is the people know very well to prove unique continuation property, very well to prove controllability, very well to prove identifiability, stability in inverse problems. The question is, I'm going to try to repeat every of these steps, but in the discrete case. Okay, I'm going to try to rewrite all the same computation, but replacing, for instance, Laplacian by discrete Laplacian. We want to have a integration by parts. We want to try rewrite an integration by parts, but in the discrete case with the discrete operators. Okay, for that reason, we need to define the interior of the mesh. We want to define also the boundaries of the mesh. Okay. For that reason, we need to define all these different sets. Okay, and what we're going to say, well, I'm going to take a derivative, but the derivative is the classical with finite difference center center finding difference for the derivative, and I'm going to take this operator with these operators in substance is an average. I'm going to take two points of the match. I'm going to consider the translated points and make I'm going to put the average operator. Okay, and also we need to define the normal because this is a square. The normal vectors are in this sense or this sense. For that reason, are 1 or -1 in some direction. Okay, and we need to consider this kind of normal conscience. Well, the first is, can repeat every step? Well, we want to try. We can define the integral of the operator. We need to define the inner product in L2. I'm going to think everything I put in an integral. I'm thinking in a discrete version of the integral. This is a Riemann function, the Riemann addition. We can take the norm and we can take the norm of the derivative. But here begin to appear the problems. The derivative does not live in the same mesh. He used the dual mesh. That means the shifted mesh. And this is the first headache in this kind of things. Okay. Well, can we make integration by parts? Of course, you can do integration by parts. It's work. But now we can see that at the beginning, I'm going to write my integration by part in one mesh, but when we pass to the derivative to the other one, we need to consider the other mesh. That means the dual mesh. This is, in some sense, I'm integrating in this black square, but when I'm going to take the mesh, I'm going to consider this other point, the x points. And this is a problem. For that reason, the computations are very hard. Okay, I'm going to pass also the average operator to the other side, but I need to pay something. The cost of this integration by parts or pass this average is to go to the other match. For that reason, every computation is a mess. But we can define the derivatives, we can define everything, and so on. Then the first step is say, yeah, okay, if somebody which works in inverse problems or Kalman estimate is, this is a Kalman estimate. What is a Kalman estimate? Okay, the classical thing is to have an operator to make a multiplication by a suitable function, okay, normally an exponential of something, and you have some parameter and you have some estimate. That means, for instance, if this is 0, that imply all these parts must be 0, and this imply a unique continuation property. Okay, but when the people use this for continuous case, in general, it's very important what happens with this parameter s. And this parameter s, the people say, well, if I take s go to infinity, I can neglect a lot of time of this one and obtain very simple, in a simple way, the unique continuation property. But these kind of Kalman estimates are true, but we need to pay something. We need to pay that the value of s is not completely free. It depends on the size of the mesh, and this is very important. Okay, and this is the main difference when you go to continuous to discrete. You need to take into account that the parameters involved in this kind of estimates are not completely free. They have a strong relationship with the size of the mesh. Okay, they say S belongs to this set. Okay, well this appear the size of the mesh S minus one. But this Kalman estimate is not completely too different to the continuous case. For that reason, you say, well, if I have this, maybe I can obtain my result of feasibility, I can obtain my result of identifiability. Okay? And what is the idea in Calderon problem? Okay? The first thing is I put Calderon problem, okay, is this one. I want to recover this quantity from the boundary measurements. Okay, and there is a very interesting problem or interesting paper where the people say, okay, study this problem is similar to study an additional one. The additional one is you can rewrite your equation with the transfer way, and instead of study divergent of Laplace of gradient of divergent of gamma gradient u is equivalent to study Laplacian plus q, where q the main idea is can we recover q from boundary measurements? This is the say. This is the problem. The problem is equivalent to Calderon one, and this estimate allows us to obtain a similar result. Okay, which is the result that we want. If all the measurements in the boundary are the same, we want to try to prove that Q is the same. Okay? And in this case, this is the Calderon problem. The Calderon problem, this say in the thing the following. I'm going to write this equation: minus Laplacian of u plus qu equals 0, and u is equal to in the boundary. And I'm going to make a second measurement. I'm going to measure the normal derivative. And the question is, if all the measurements are equal in the boundary, does imply that the q is equal? This is another problem. Well, we're going to try to rewrite the same problem, but in the discrete case. If I'm going to write this equation, minus discrete Laplacian u plus qu equals 0 in omega. Omega is a discrete domain. And u is equal t in the boundary. And I'm going to take these measurements, and I want to recover q. What we can say? Okay. Well, the idea is the following. The thing that I'm going to try to recover is the following. For instance, if all the measurements in the boundary are equal, q is equal. This is interferability. Or the second one is if I have two function q, and all the measurements are close, that implies that q are close. This is the question. Okay. To understand or to answer this problem, Asala, Paivarintan, and in the works of Ullmann appear some technique to prove this one. To prove this one, they use something called complex geometric optics. What means this? Okay, I'm going to write this equation. If q is equal 0, the solution is a plane wave. If q equals 0, the solution is this exponential with eta verified in this condition. For that reason, if I put q, I'm going to assume that the solution can be written as a solution of without q plus a rest. And the main idea is the following. I'm going to try to estimate how far these are if the measurements are close. Okay. This function, this way to write the solution, are called CGO, complex geometric optics. Okay, and I'm going to try to pass a few, and the main result is the following. The result says something like this: if I'm going to take two function q, okay, then the solutions have this estimate. What say this estimate? Say that if the measurements are close, these two terms almost must be close. But not only that, we need to pay the cost, and the cost that we need to pay is the size of the mesh. Okay, that can be obtained, but only the result if the mesh has a suitable size. Okay, if this does not verify this condition, this is not true. Okay, and the other thing is this result is very agree with the results of Alessandrini, because the results of Alessandrini say, okay, the estimates are logarithmic. Okay, let me say what means this. If the logarithmic of these estimates are close, then the solutions are close. Okay, but when you go to numerical, in the numerical point of view, this is very bad because a logarithmic estimate for numerical is very poor. For that reason, in general, these kind of problems are so-called ill-posed problems. They are not well-posed problems. Okay. Well, what is the main idea on this one? Well, the first thing is thanks to the unique continuation estimate, thanks to the Kalema estimate, it is possible to repeat the case, the continuous case, constructing this CEO solution. But this implies, well, numerically, I don't know what happened. But at the beginning, I can say theoretically it is possible to do this, but is this allow us to obtain some numerical way to reconstruction. That means some numerical way to recover the conductivity. Okay, this is the main idea of the results. Okay, I don't go to the proof of the estimate because it's very technical. But I'm going to try to give you more the idea of this one. Okay. Well, the these kind of results not only are true for Laplacian also. I know that in Brazil there is a long community working in this perceived equation. That this problem can be done also for this perceived equation. Okay. For instance, one case is the BBO equation, the BBM equation, where you have where there are a lot of results for the continuous one. The classical is the Benjamin Bonamahony, but there is result of Lionel Rossier, which is a good friend of several people in Brazil. Okay, and and there is a long community of Felipe Linares and people in IMPA, in Campinas, and so on, which were in this kind of problem. And the main idea is we can write the BBM equation. Okay, we can go, for instance, to the linear case, and we can go to ask the same question. I have this equation. I'm going to a potential alpha here, and the main question is: if I have enough measurements in the boundary, it is possible to recover alpha, for instance. And the question is: yes, it's true, it's possible, but we need to prove yes, we can go to rewrite in a discrete way, and it's possible to obtain some Kahneman estimate for this equation, but only we need to pay a price, and the price is the parameter S, which appears here, has a strong relation with the size of the mesh. Okay, and with these Kahneman estimates, you can obtain some results of controllability and invert problem also. Okay, but uh, this is a quite new area of research. There is a lot of open problems, but and the computations are very hard. Okay, but I'm going to let open the questions or discussions. Okay. I have in this moment we we have more questions than answers. Sorry, but maybe more interesting the question than the answers. Okay, I'm going to pass this one to don't go to the technical details. Thanks a lot.